Hi all, we are on the 13th lecture of the quantum mechanics. So this particular lecture, I will be dealing with the different properties of Hermitian operator. So we can prove it one by one. So the first property of Hermitian operator is their eigen values are real. So the first property of a Hermitian operator. Okay, then how will you prove it? Okay. Now, in order to prove it, the first thing is we should recall what is known by a Hermitian operator. Recall. So if A is Hermitian operator, then the inner product psi A chi, where psi and chi are two vectors in the vector space, would be equal to the inner product chi A psi, the complex conjugate. Okay, so actually we should do we have to write A dagger here, but since it is a Hermitian operator, A dagger is same as A. So this is the definition of Hermitian operator. Now with this definition, we can show that the eigenvalues of the Hermitian operators would be real quantity. Okay. Now for that, okay, let us suppose A is Hermitian operator. Okay, so A is Hermitian operator. Then let the ket phi is eigenvector of A corresponding to eigenvalue lambda. And how can we write this eigenvalue equation? The operator A acting on ket phi equal lambda times ket phi. Now just take the inner product on both sides with phi, then phi A phi would be equal to that can be written as according to our the Hermitian property, the inner product phi A phi can also be written as phi A phi complex conjugate. So actually what we have done is we have used this result. Okay. So if you interchange the bra phi to ket phi and ket phi to bra phi, you have to take a complex conjugate, and there is no need to change A if A is Hermitian. Now, what is the result of A acting on ket phi? The A acting on ket phi is lambda ket phi. And here is again, A acting on ket phi is lambda ket phi. Now I can take lambda outside. So lambda phi phi. Here also I can take lambda outside. So lambda phi phi, but there is a complex conjugate all over. So this is equal to lambda star phi phi complex conjugate. So this is simply equal to lambda star the inner product phi phi. Okay, so you can change. You can do this complex conjugation. Then you have to just interchange the bra and kets. So finally, so this is your left side. This is your right side. So take both the things on one side. Then what will you get? Lambda minus lambda star inner product phi phi would be 0. So how is it possible? Because this inner product phi phi cannot be 0. The inner product phi phi cannot be 0 because that is a norm of a vector. The norm of a vector would be always a positive quantity. It would be 0 only if it's a 0 vector. Otherwise, it would be non-zero. Okay. So this it will be non-zero except for 0 vectors. The vectors, the 0 vectors are vectors with 0 norm. 0 vectors means 0 norm vectors. Okay. Now, the zero norm vectors cannot be a non-trivial eigenvector. Okay, so there is it is a trivial situation. That is, this 5 becomes 0. There is a trivial situation that can be neglected. So usually, the inner product 5 would be non-zero because the norm of the vector would be non-zero. Okay, for non-zero vectors. So then, in order to satisfy this condition, then the only possibility is lambda minus lambda star equal to 0, or lambda star must be equal to lambda. So that is a complex conjugate of the scalar must be equal to that scalar itself. So this would be true only if this lambda is not having the complex part. Okay, so this means that lambda cannot have complex part. In other words, I can say that lambda must be a real number. Okay, so what is the lambda here? So lambda is the eigenvalue of the operator A, and we have proved that the lambda is real. It's great. Okay, so very simply we have proved that the eigenvalue of the Hermitian operator must be real. So this we have proved. Next, we can go for the second property of Hermitian operator. The second property of Hermitian operator is the eigenvector corresponding to different eigenvalues are orthogonal. So eigenvector corresponding to different eigenvalues are orthogonal for the Hermitian operator. Okay, then again, we can start from Hermitian operator A. So consider Hermitian operator A. With eigenvalues lambda 1, lambda 2, lambda 3, etc. up to lambda n, and eigenvectors vector phi 1, vector phi 2, etc. up to vector phi n, such that the operator A acting on the vector phi I gives lambda I times phi I. Okay, now we already proved that all these lambda I are real, because since A is Hermitian operator. Okay, now we can take some inner product between some phi I A phi j. Now, according to the property of Hermitian operator, this would also be same as the inner product phi j A phi I complex conjugate. Okay, it's a very simple thing. So I've just interchanged the bra and ket vectors. I have to take complex conjugate, and there is no need to put a dagger here. The reason is A is Hermitian. A dagger is same as A. Now, what is A acting on phi j? The A acting on phi j would give lambda j times phi j according to this equation. Then on the right side, phi j, A acting on phi I would give lambda I times phi I. Again, it is a complex conjugate. Now lambda j can be taken outside, so this can be as lambda j, the inner product phi I phi j equals Here again, lambda I can be taken outside. So lambda I, there is a complex conjugate common. Then phi j, phi I complex conjugate. Now this phi j, phi I complex conjugate can be written as phi I, phi j. And this, since lambdas are real, lambda I star can be written as lambda I. So this is lambda I. And I can just interchange the order. The phi j, phi I, the complex conjugate can be written as the inner bracket phi I, phi j. So this is your left side, the right side. You can take both the things on one side. Then can be written as lambda j minus lambda I times the inner bracket phi I, phi j equals 0. Okay. Now this must be 0. Now if the eigenvalues are different, then lambda j must not be equal to lambda I. So that means lambda j minus lambda I cannot be 0. Then how this equation would be valid? So if eigenvalues are different, if lambda j is not equal to lambda I, then the only possibility is your inner product phi I, phi j must be 0. Then the inner product phi I, phi j must be 0. So that means the vectors phi I, phi j's are orthogonal. Now again, recall this phi I, phi j's are the eigenvectors of the Hermitian operator corresponding to the eigenvalues lambda j and lambda I. So this shows that the eigenvectors corresponding to the different eigenvalues are orthogonal. So this is a very simple proof of the orthogonality condition of the eigenvectors of Hermitian operators. Okay. Now the third property is, now we have already listed that in case of n-dimensional vector space, and Hermitian operator A can have total of n eigenvectors. Now these n eigenvectors, if since lambda 1, lambda 2, lambda 3, if they are different, then we'll be having n different eigenvectors. They are orthogonal to each other. So phi 1 would be orthogonal to phi 2, phi 2 would be orthogonal to phi 3, etc. And all eigenvectors would be orthogonal to each other. Okay, so that means the set of eigenvectors of Hermitian operators are nothing but the set of linearly independent vectors. Now the set of linearly independent vectors can be treated as a basis. Okay, so that is the third property of the Hermitian operator. The set of all eigenvectors of a bounded Hermitian operator forms a complete set. Complete set means it forms the basis. Okay, again I'll explain. So consider an Hermitian operator A. Then if their eigenvalues are lambda 1, lambda 2, etc. up to lambda n, with corresponding eigenvectors phi 1, phi 2, etc. up to phi n. Recall this phi I, phi j would be equal to 0 when I not equal to j. So that means all eigenvectors of the Hermitian operator A are orthogonal to each other. So that means this set phi I, the set phi I is the set phi 1, phi 2, phi 3, etc. up to phi n are linearly independent vectors. Now the collection of all linearly independent vectors or a set of all linearly independent vectors forms a basis, and that forms a complete set. That means you can express any other vector in that space, the vector space, in terms of these basis vectors, or in terms of the eigenvectors of the Hermitian operator. So that forms a complete set, or it forms the basis. Okay, so that is a simple definition of basis or complete set. So in order to find the basis or complete set of a vector space, only thing is what you have to do is you have to just find the eigenvectors of a Hermitian operator in that vector space. Okay. So that's all for the time being. So in the next class, I'll be introducing the transformation of the operators and vectors. It's called similarity transformation in case of the normal vector spaces, and in the complex vector spaces, it is called the unitary transformations. Okay, so those things we'll be discussing in the next class. Okay, so for the time being, we can stop here. We'll see later. Bye.